Okay, another kind of approach is using, instead of pulse width modulation control, we are using frequency modulation control. So what happens that for the same comparator, so V carrier and V reference, so just now we adjust the V reference, but now we are adjusting the carrier, the sawtooth. The term is the same, duty cycle, the time and the modulation is the same, but now we are adjusting in terms of the carrier. So what happens that we squeeze the sawtooth here. Instead of maybe the frequency now is 20 kilohertz, we reduce into, let's say, higher pulses in one cycle. So it becomes 40 kilohertz like that. Or we expand in terms of their so when we squeeze, so we shall have a more pulses inside our one frame, so it become more pulses generate to the switch, so the output or V out will increase. And when we expand in terms of their frequency, so maybe in one cycle we have only few pulses, so in terms of 20 kilohertz maybe reduced to 10 kilohertz, so V out may reduce. So just now we are, for PWM, we are adjusting V reference upper or lower, but now for frequency modulation we are adjusting the carrier. Means that in terms of their carrier, maybe the frequency become higher or lower. Higher frequency, the V out increase. Lower frequency, the V out will decrease. So this is the control approach of frequency modulation control. So again, the switch mode regulator. So the switch mode regulator can be used to convert the unregulated into regulated output voltage. So this is the main concept how the regulator works. So the unregulated into regulated required output voltage. So the regulation can be achieved by controlling duty cycle. So in this PWM, the frequency is fixed, or we can adjust the cycle using frequency modulation control. So the switching device or the power switch that can be used is the same, either bipolar junction transistor, normal one, MOSFET, IGBT, HEXFET or whatsoever. All are listed here are the power switch that can be used in the higher power processing current. So in terms of their mode, so we can distinguish between the operation later on the regulator that producing CCM, continuous current conduction mode, or DCM, discontinuous current conduction mode. So in practice, we can operate both modes together, which both modes have actually the different characteristics. So we have a few types, which is basic types of switching regulators in the market, which are using a system of buck converter, referring to the step down kind of conversion, or boost, which refer to the step up boost converter, or can be step up and step down as well, which is referring to a buck boost or chuck regulator. So we shall take a look in specific device or specific system accordingly. So for the buck converter, we produce a lower voltage compared to the input. So the application is on the DC power supplies and for DC motor speed control. So we have a fixed source, we have a variable output voltage load. So the output average will be how much duty cycle that we apply to the system, or to the switch times the source peak voltage. So this is the V out average. So the V out average will be dependent on the how much duty cycle it will varies on the system. So if we adjust to this certain amount of duty cycle, so we shall see that the V out here, the dotted line referring to the V out. So we squeeze narrower in terms of our duty cycle, so the VS will reduce accordingly. So the maximum is 100% duty cycle, minimum is 0. Okay, when the ratio of the switch is varied, so the output also varied, so we can control the output using the duty cycle. But in practical, there are two disadvantages of the circuit, which is the load may be inductive. So even in a resistive load, there will be always a straight inductance. So it will be more worsen if we have inductive load. So the switch has to be the switch itself have to absorb the inductive energy. So it means that we have a spike on the switch during switch on and off, and especially in the inductive load. So the output voltage also will fluctuate between 0 and Vs. We have a spike. So the spike we have to eliminate, or we have to filter such that the voltage spike, this is referring to the current spike or current this continuous flow. This is referring to the spike of the voltage. Sometimes if you rate or you select the switch which is too narrow in terms of their blocking voltage, so you might damage your switch when the voltage spike happen. So solution for the problem is that we should insert a freewheeling diode to control the inductive current issues, or we have to use low pass filter to minimize the output voltage fluctuation. So this is the arrangement of low pass filter to the circuit. So when the switch is on, the diode become reverse bias. So the input will provide energy to the load and inductor. Switch on here, it will go to the load. But when you switch off, there still will be current inside our sorry, this is for low pass filter. If you switch on, there will be high spike. So the high spike will go into your capacitor instead of going direct to your load. It will absorb the capacitor first, then it go to your load. Then when you switch off, there will be a remaining current inside your load, so it will revert to the source and the switch. And so what happens now, if you provide a freewheeling diode, the remaining current will flow to the diode and also circulate into the load until it disappears. So this is the ideal output in terms of voltage, and should be switched on and switched off smoothly. But in actual, when you switch off, there will be spike here, spike down instead of reverse spike, then it goes back to the 0. You switch on and we switch off, there will be a spike here. So during simulation, you can see the issues. You can appreciate the issues actually. So when switch is off, inductor current flows through diode and transfer to the diode here and transfer to the load until it diminishes. So continuous connection mode, CCM. So during CCM, so what means by CCM is that continuous current mode. The current will be flying on the positive side always. There will be no current return to 0. The current will be maintained at positive. It will be maintained at positive. For DCM, the current will have a current, but at a certain time there will be no current inside the circuit. But for CCM, the current will be continuously flow and appear on the circuit. So assume that the current is already the circuit is at steady state. If the circuit is initially starting, it will start at 0, but we assume that the analysis taken place at the steady state. So we have I min and I max, I in min, I in max. So the flowing or the min and I max during switch on at steady state, switch on. So we have here Vs divided by minus Vo. So this is the load that we measure here. In terms of current, so you fly between minimum I in min and increase to the maximum. When you adjust the duty cycle, actually the maximum will be adjusted accordingly. But we assume that this is the setting of the duty cycle right now. So once you reach duty cycle, you switch off. So this is the maximum value of your I in. So we start from minimum to the maximum. Once you switch off, it will reduce accordingly, and it will reduce from maximum to minimum throughout the load as well, and returning back through the diode. So diode here is forward bias, is considered as short circuit. Just now we have diode here also, but when the current flows here, the diode is open circuit, so you cannot see here. It's just eliminate from here. But when a reverse bias, means that the current flows here to the circuit for on time, and off time the path is taken out, so the current will be flows also here, and it will not go back to the source because the switch already open. So we will return to the load through the diode here. So the place of diode is imagined or visualized as a short circuit. So still you have a current that flows into your load. So the current flows to the load and it will reduce because the storage current is already absorbed by the load. So the amount will reduce, and it start again to rise up when the next cycles begin from minimum to maximum. So the difference between maximum and minimum magnitude is so-called delta I load. So or the ripple level. So in this circuit, we consider this kind of consideration. It happened in steady state. The assumption is that the inductor current flows continuously and always positive. As I told you before, the current is always at positive level. So the average inductor voltage and capacitor current are 0 because inductor and capacitor, they are not load. So they are not storage, and they are energy storage. They are not load. So they just absorb and release. For inductor, it absorb and release the current. For capacitor, it absorb and release the voltage. So the current and voltage are 0. In terms of the average current and voltage are 0. So also we assume that, so this for this CCM, we assume that the components are all ideal. Means that the power supply by the source or delivered to the load is not diminished or being absorbed or being used by inductor or capacitor. All the current power from the source is delivered to the load. So when switch is closed, the switch conduct the inductor current and diode become reverse bias. So this results in positive inductor voltage. So the voltage cause a linear increase in inductor current of, so this is the amount of load voltage, which is V source divided by V output. So the ripple here is amount of V source minus V output divided by L times dt. So this formula used to determine how much the ripple range in terms of, or what value of inductor you want to use, because when you design a circuit or a schematic or a system, this is the amount that you need to accomplish. Some customer or some device, they need a lower ripple current, so the lower ripple current will be the higher inductor you have to put in. Okay, so this is the amount of the spike of your current. So this is the amount of your ripple current value. So when the switch is open, just now when the switch is off, switch is open,